Swayam Prabha. Digital India. Educated India.
Welcome to this new module on advanced welding processes under the course Advanced Manufacturing Processes. In the previous modules, we have discussed about advanced casting processes in the module 1, then the advanced machining processes. In this module, module 4, we will be discussing about some of the advanced welding processes. The conventional welding processes like arc welding and gas welding serve variety of purposes. Yet, there are requirements when we need to apply newer welding processes to cater to some specific requirements as mentioned below. These are joining of thick plates, structures and large joints. Then joining of very thin plates can cause large heat affected zones and undesired warpage and uneven joints. This eventually may spoil the workpieces completely. Then joining of different metals can cause uneven fusion due to different ranges in melting points. Requirements of good finish, low heat affected zones and high quality weld demand use of advanced or non-conventional welding methods. In order to cater to these requirements, the following newer welding processes have come into existence. Number 1, submerged arc welding. 2, projection welding. 3, solid state welding. 4, electron beam welding. 5, laser beam welding. 6, friction stir welding. 7, adhesive joining and 8, microwave joining. These processes will now be discussed one by one. Let us first discuss submerged arc welding. This process was invented in the United States of America and the erstwhile Soviet Union in around 1930s. The process contributes to approximately 10% of the total welding activities being carried out worldwide. In this process, the arc is submerged under a blanket of flux, hence it is not visible from outside. The schematic is shown in the screen. So, this is the common submerged arc welding process, in which this is the flux what we were talking about and the arc will be in between this, beneath this, which will be not visible otherwise. And this is the welding weir through which the arc will be produced and this weir will get melted and deposited here. Therefore, this end, this will be automatic feed for the weir. Through this end, the weir will be fed into the position of the arc and this will be the power supply to this and to this electrode. The other point of the power will be connected to the work through this. Thus, this will be moving during the welding process. So, here in this particular case it is being shown, it is moving from this to this, and therefore, the welding will be carried out, or the fusion of the material will take place on the part of this travel of this electric wear, this welding wear, and this flux will cover this arc at this point of welding. These are other arrangements for holding the workpiece as well as for the movement of the welding torch, we can say. Now, let us talk about the principles of operation of the submerged arc welding process. In this process, the end of the continuous bare wear electrode is inserted into a mold of flux that covers the area or joint to be welded. An arc is initiated using some of the common arc starting methods. A wear feed mechanism then begins to feed the electrode wear towards the joint at a controlled rate, and the feeder is moved manually or automatically along the weld seam. This is what we have just seen in the figure and we have already discussed. For machine welding or automatic welding, the work may be moved beneath a stationary wear feeder. Additional flux is continually fed in front of and around the electrode, and it is continually distributed over the joint through the hopper. Heat evolved by the electric arc progressively melts some of the flux, the end of the wear and the adjacent edges of the base metal, which creates a pool of molten metal beneath a layer of liquid slag. The molten butt near the arc is in a highly turbulent state. Gas bubbles are quickly swept to the surface of the pool. The flux floats on the molten metal and completely seals the welding zone from the atmosphere. The flux blanket on the top surface of the weld pool prevents atmospheric gases from containing the weld metal. It dissolves impurities in the base metal and electrode and floats them to the surface. The flux can also add or remove certain alloying elements to or from the weld metal. As the welding zone progresses along the seam, the weld metal and then the liquid flux cool and solidify, forming a weld bead and a protective slag over it. However, it is important that the slag is completely removed before making another weld pass. Now, let us see the factors which determine the usage of submerged arc welding. These factors include: number 1, the chemical composition and mechanical properties required of the final deposit. Number 2, the thickness of the base metal to be welded. Number 3, joint accessibility. Number 4, position in which the weld is to be made. Number 5, frequency and or volume of welding to be performed. Now, let us look at the characteristics of submerged arc welding process. This process is known for higher metal deposition rate, higher welding speed. The process has higher process efficiency, lower nitrogen and hydrogen content in the weld metal, cleaner weld metal. The process has better control over the chemical composition and better control over on the mechanical and metallurgical properties. Now, let us talk about the general methods of submerged arc welding process. The process can be carried out in 3 different modes, namely semi-automatic mode, automatic mode and machine mode. Each method requires that the workpiece be positioned such that the flux and the molten weld pool will remain in place until they are solidified. Many fixers and positioning equipment can be used for typical requirements like this. Now, let us talk about the semi-automatic welding mode. It is carried out with a handheld welding gun, which delivers both flux and the electrode. The electrode is driven by a wear feeder. The flux may be supplied by a gravity hopper mounted on the gun or pressure fed through a hose. This method features manual guidance using relatively small diameter electrodes and moderate travel speeds. The travel may be manual or driven by a small gun which is mounted with a driving motor. Now, let us see the automatic welding process. This process is carried out with equipment that performs the welding operation without an operator to continually monitor and adjust the controls. Expensive self-regulating equipment are used in order to achieve high production rates in this welding method. Then finally, to the machine welding method. This employs an equipment which perform the complete welding operations. It only needs monitoring for positioning the work, start and stop welding, adjust the controls and speeds of each weld. Submerged arc welding requires some edge preparations and provision for backup strips for effective welds to take place. The details of these are indicated in the next figure and the process parameters are indicated in the next table. So, this is a basic configuration used in submerged arc welding process as shown in the screen. So, these are the 2 base materials. So, they are positioned like this, where in this portion the welding is to be carried out and the thickness of these base materials is T and W is the width of the backing strip. Just now we were talking about one backing strip is required for effective welding in this process, and this is what is the width of this backing strip, that we can easily understand from this configuration, that this width must be greater than the joint width, and this S is the separation between these 2 base metals. So, this table shows the parameters used in submerged arc welding process. So, this talks about the thickness of the plate, then what should be the root opening, the current required, then DCEP, which is called direct current electrode positive voltage, then the travel speed, then electrode diameter, electrode consumption, then the thickness and the width. So, here different parameters, say for example, for a plate thickness of 3.6 millimeter, root opening generally is taken to be 1.6 mm, current applied is 650 amperes, DCEP voltage is 28 volts, then travel speed is set at 20 millimeter per second, then electrode diameter used is generally 3.2 millimeter, whereas the electrode consumption rate is 0.11 kg per meter, and then the time for this welding to be carried out is 3.2 minute and the width is 15 millimeter. Similarly, for other plate thicknesses like 4.8, 6.4, 9.5, 12.7 etc., are given in this particular table, and this can be calculated or can from experimental data this can be arrived at. Now, let us talk about one of the most important components in this system, that is flux. Flux is a material used to prevent, dissolve or facilitate removal of oxides and other undesirable substances. It helps in the following functions. Number 1, it protects the weld pool from the oxidizing agents or the oxidizing environment. It provides appropriate chemical composition as desired. Then it helps in improving the properties by alloying materials appropriately. That means, we can add few materials in terms of flux also, or through the use of flux also. It helps in deoxidizing the weld metal. It helps in improving weld bed shape parameters. It also helps improving the efficiency of metal deposition and stabilizing the arc. Let us talk about another important component in the system, that is power sources. These power sources play a major operating role in the submerged arc welding process. Generally, a DC power supply may be a transformer rectifier, a motor or engine generator which provides a constant voltage, constant current, or a selectable constant voltage, constant current output. AC power supplies are generally transformer types and may provide either a constant current output or a constant voltage square wave output. Since submerged arc welding process is generally a high current with a high duty cycle, therefore, a power supply capable of providing high amperage at 100% duty cycle is recommended. DC constant voltage power sources. These power sources are available in both transformer rectifier and motor generator models. These range in size from 400 ampere to 1500 ampere models. These power sources are used for semi-automatic submerged arc welding at currents ranging from 300 ampere to 600 ampere, recommended for 1.6 to 2.4 millimeter diameter electrodes. As we have already discussed, size of the electrodes, that is diameter of the electrode, is also one of the important parameters to be considered. The automatic welding is done with currents ranging from 300 to over 1000 amperes, with wears generally ranging from 2.4 to 6.4 millimeters. Applications for DC welding at over 1000 ampere are limited, since severe arc blow can occur at such high currents. New generation power supplies provide more stable arc and can be maintained at lower current densities. A constant voltage power supply is self-regulating, so that it can be used with a constant speed wear feeder. No voltage or current sensing is required to maintain a stable arc. Hence, very simple wear feed controls may be used, which are the most commonly used supplies for submerged arc welding. Constant current DC power sources are available in both transformer rectifier and motor generator models, with rated outputs up to 1500 ampere. Now, let us see the alternating current power sources. Transformers are the most commonly used power sources in AC welding. Sources rated for 800 to 1500 ampere at 100% duty cycle are generally available. If higher amperages are required, these machines can be connected in parallel also. Conventional AC power sources are the constant current type sources. The most common uses of an AC power for submerged arc welding are high current applications, multi-wear applications, narrow gap welding, and applications where arc blow is a problem. As we have already discussed, in DC power sources there may be severe problem of arc blow, which should be avoided at any cost. Now, let us see another important component in the system, that is controls. The control system used for semi-automatic submerged arc welding process is composed of simple wear feed speed controls. Controls used with constant voltage power supplies maintain a constant wear speed feed. Controls are used with constant current back loop. These controls are interfaced with the power supply wear feed motor in order to maintain the welding voltage and wear speed at preset values. The greater advantage of digital controls is their precise control of the welding process. The disadvantages are that the controls are not compatible with some power supplies and they are slightly less rugged than most analog controls. Digital controls are currently available only for use with constant voltage power supplies. These controls provide wear feed speed adjustments, that is current control, then power supply adjustments, that is voltage control, and weld start stop, automatic and manual travel on offs. Also cold wear feed up downs, run in and crater fill controls, burn back and flux feed on offs, digital current, voltage and wear feed speed meters are standardized on digital controls. These are some of the control aspects that we can obtain through the control unit. Analog controls are available with use for both constant voltage and constant current power supplies. Basic control consists of a wire feed speed control, which adjusts current in constant voltage systems and controls voltage in constant current systems. A power supply control which adjusts voltage in constant voltage system and adjusts current in constant current system. A weld start stop switch, automatic or manual travel on off, and cold wire feed up down facilities are also available. These controls have the same advantage as analog controls for semi-automatic submerged arc welding process. These are, however, prone to drift and do not allow precise process control. Now, let us see some effect on the polarity. The welding can be operated in the following two polarity configurations. As we have already indicated, one is direct current electrode negative mode, in which the electrode is connected to the negative terminal of the power source. It gives higher deposition rate, higher yield strength and higher hardness. And the other mode is direct current electrode positive mode, DCEP. It provides lower deposition rates and lower yield strength. Now, let us look at other accessories and equipment. With submerged arc welding, the commonly used accessories are travel equipment, flux recovery units, fixturing equipment and positioning equipment. Let us look at the travel equipment. Weld head travel in submerged arc welding is generally provided by a tractor type carriage, a side beam carriage and a manipulator. A tractor type carriage provides travel along straight or gently curved weld joints by riding on tracks set up along the joint or by riding on the workpiece itself. Some guiding wheels or mechanical joint tracking devices are also used. Side beam carriages provide linear travel only with rated speed travels. They are fixed and the workpieces must be brought to the weld station. Its greatest use is for shop welding. Manipulators are similar to side beams in that they are fixed and the workpiece hand side must be brought to the welder. Manipulators are more versatile than side beams in that they are capable of linear movement in 3 axes. The weld head wear flux hopper and often the control and operator ride on the manipulator itself. Next is the flux recovery unit. These units are frequently used to maximize flux utilization and minimize manual cleanup activities. Flux recovery units may do any combination of the following: remove unfused flux and fused slag behind a weld head. Then next is screen out fused slag and other oversized material. Next is remove magnetic particles. Next, recirculate flux back to a hopper for reuse, and lastly the heat flux in a hopper to keep it dry. Pneumatic flux feeding is commonly used in semi-automatic SAW and frequently used in automatic submerged arc welding process. Next components are positioners and fixers. Since submerged arc welding is limited to flat position welding, positioners and related fixturing equipment find widespread use for it. The commonly used positioners include head tailstock units, turning rolls or boat to rotate cylindrical parts under the weld head, tilting rotating positioners to bring the area to be welded on irregular parts into the flat position. Then custom fixturing often includes positioner to aid in setting up, positioning and holding the workpiece together. Testing requirements for submerged arc welding welds. Number 1, destructive testing. These testing include tensile testing and impact testing. As we know, in both these cases the specimen or the weld joint is to be destroyed and the corresponding strength, tensile strength and the impact strength are measured. The other category is non-destructive testing. This category include surface inspection through die penetration test, magnetic particle inspection test, etc. Then another category of inspection is internal inspection method, which include ultrasonic inspection and radiographic inspection. Through these methods, one can assess whether there is some cracks or holes inside the welded portion. Now, let us look at the submerged arc welding applications. This welding finds applications in the following. Number 1, while welding high strength low alloy steels, then for welding low carbon steels, for welding stainless steels, this method is or this submerged arc welding process is found to be suitable. For welding aluminum alloys, titanium alloys and other non-ferrous alloys, this method can be suitably used. Then fabrication of thick plates, then thick pipes and pressure vessels, also this submerged arc welding is commonly used. Then for welding of railroad tanks, ships, heat exchangers, then overlaying, this method is used. A common submerged arc welding application is in the welding of cylinders, the home gas cylinders, in which as shown in the screen, this joint is made through submerged arc welding process. Now, let us summarize what we have discussed in this particular session. In this session, we have discussed in detail about the requirements of advanced welding methods and the submerged arc welding process. The details of the process have been discussed along with its requirements, features and applications. We have also seen that this method can be carried out in two different modes, that is DCEN, direct current electrode negative, and DCEP, direct current electrode positive. Moreover, we have seen the applications of this process and is found to be very versatile as far as the joining or welding of the engineering most common engineering materials are concerned. These materials include both ferrous as well as non-ferrous materials like aluminum, titanium, alloys, etc. We hope this session was useful and interesting. Thank you.